Okay, and welcome you to today's March MicroObservatory Monday. We thought we'd take a tour of the lab where the telescopes get maintained by Frank. And if I turn my camera, here's Frank. There we go. And he'll be showing some parts of the telescope that you see in the other camera in a little bit. So just a little bit of background on the MicroObservatory network. It's actually one of the first robotic telescope networks in everyday use by students and the public. It's been, I think, online, one of the telescopes, pretty much since 1998. No, now 2002 now or something.
Continuously online, more or less, give or take a week, since 98.
Right. So
98, 97.
Right. So for 20 years, we've been online. So the telescopes are getting a little long in the tooth, but Frank does a great job keeping them maintained. And to date, we're still the telescope used by the most pre-college users. We have about 30,000 people using the telescopes each year, taking somewhere between 50 and 100,000 images each year. And you guys are a big part of that audience. So what we're going to do today is try and give you information, so that one of the things we've found through our research is that the more students understand that there's a real physical machine at the other end of their clicks of taking images, the more they understand how astronomical observation works. And actually, some of our research with the Youth Astronet students is suggesting that the more they use the telescopes and the image processing, those students who use it most end up showing the most pre-post gain in those measures of, I think of myself as a scientist, and other people think of me as a scientist, and also those selectors of STEM career. So our telescopes, there's 5 that were all built in the 90s, and here they are in the bottom of the slide, when also cameras had very low resolution digital cameras, so it's not a great image. But there's 5 telescopes known as telescope 1, 2, 3, 4, and 5, or A, B, C, D, and E, or Annie, Ben, Cecilia, Donald, and Ed. And in the educator portal, actually under the curriculum resources, there's a PDF about the telescope's names, but they're named after really kind of hidden figures in astronomy, if you will. The telescope 1, Annie, is named after Annie Jump Cannon, who you see in the upper left here. And she worked actually right below the lab where Frank and I are sitting, in the Harvard plate stacks, as one of the women computers. They were called computers in the late 19th century and early 20th century. They carefully examined thousands and hundreds of thousands of glass plates. Here you see Annie Jump Cannon. There's a glass plate right here propped up. And she's actually really well known for developing the classification scheme for stellar spectra. Those of you who might know about the spectra of stars, stars are rated from hottest stars to coolest stars by letters O, B, A, G, F, K, M. And Annie Jump Cannon is the scientist, the woman computer who really examined those spectra and classified those different categories of stars. Telescope Ben is named after mathematician and astronomer Benjamin Banneker, who was contemporaneous with Thomas Jefferson. He actually did a lot of surveying for the city of Washington, D.C., and he created almanacs of celestial positions. He actually predicted a lot of solar eclipses more accurately than the almanacs of the time. So our telescope Ben is named after this famous African-American astronomer. He's actually also known for his letters to Thomas Jefferson, where he actually took criticized Jefferson's pro-slavery views. So he was quite scientist and citizen who contributed a lot to astronomy and other fields. So that's Ben. Cecilia is in the lower right here, named after Cecilia Payne Gaposchkin, once she was married, and she is hailed as having written, and still to this day, possibly the most brilliant astronomy PhD thesis. She actually also looked at the spectra of stars and the sun and noted that the spectra of the sun seemed to indicate, she used the kind of evolving science of physics and understanding the atomic structure based on spectra to note that the sun seemed to be mostly hydrogen and helium, although at the time the leading astronomers, mostly male at the time, told her to kind of back off that assertion in her thesis because they thought the sun's composition had to be closer to the Earth's composition. It couldn't be just hydrogen and helium. But we know now that, in fact, her supposition at the time was, in fact, correct. And is one of the key ideas behind understanding that all the stars in the universe are composed of the material hydrogen and helium that mostly came from the Big Bang. So she's a very famous female astronomer. Donald is probably our very hidden figure. Less people have probably heard of him. Donald Menzel, he's in the lower left here. He was a director of the observatory here. And he actually is one of the first astrophysicists, actually like Cecilia Payne Gaposchkin, in that he really applied physics and chemistry to understanding the stars, and especially understanding the sun. And he was also a debunker of UFOs. So he and these Peterson, Frank points out these Peterson field guides. The one for stars and planets was actually co-authored by Donald Menzel.
The original author.
He's the original author. Jay Peskoff probably
a student of his.
Okay, his student joined the second edition.
Like bird guides.
Yeah, so that's Donald, and then Ed, Telescope Ed, which is on the roof. Where is it? On the roof. Oh my goodness! Ed has just arrived on the roof. Is right here, and he was also a director of the Harvard College Observatory, but it may be that his biggest contribution to astronomy was actually hiring the group of women computers in the plate stacks, and you can see them all here. Number of the Harvard women astronomers who made from Annie Jump Cannon to Henrietta Leavitt, who discovered variable stars that are really like standard candles for distances in the universe. These to Wilhelmina Fleming, these women scientists in Ed Pickering's labs really contributed a lot to astronomy. So that's who our 5 telescopes are named after. And we are going to, I'll actually go look at that later. I'm gonna stop my screen share because we're gonna go take a look at one of the telescopes that's in the lab. And I'm gonna I'm actually gonna bring this over to Frank. And so that Frank's gonna give us a little tour of what happens in the lab and some of the parts of the telescope that you and your students actually physically control when you're using the telescope.
So welcome to my desk environment and lab space. This is where the telescopes come back from the field, whether from the roof here, Arizona, and these have been situated on the mountain top in Hawaii and in Australia in prior years. And maybe we'll be returning to southern skies in the next year or so. So are you able to hear me? I think so. Yeah. So pipe up if you can't. So I'll try to talk louder if I'm mumbling too much. So right in front of me is Annie, who has not been observing the skies for actually many months. It had some troubles, and we've been slowly fixing those, repairing those, replacing those, and getting this back into service. But they come from the field and they come here, and they actually come in a shipping crate. If Mary can turn around. This shipping crate here, actually, it's a, actually, I guess put a body in it if you wanted to. But these telescopes were purposely built so they can be packed in a crate like this. And FedEx and other world delivery services can actually drop ship this anywhere in the world within 3 days. We pack it up with foam, and it's protected quite well. And we have these little fragile stickers all over it. They come pick it up here and drop it, and helpers at individual observatories will position and situate the telescope itself, essentially from this part of the telescope on up, onto a tripod that's situated at the observatory where we are hosted. And we screw it down and plug it in. And this cable here provides communications and powers to the unit. So essentially anywhere in the world, we can actually drop one of these telescopes to observe the skies. They're ideally suited for the middle latitudes. So what are the main parts of the telescope? So we told you about the foundation. Just like building a house, you want a strong foundation. The telescope is an equatorially mounted instrument, which means if we align the axis upon which the telescope tracks the stars with the spin axis of our Earth, all we have to do is move the motor at the same rate in which the Earth turns, just in the opposite direction, so that the telescope is tracking the stars that rise in the east and set in the west. And that's this axis right here. This is the right ascension axis here. So as long as this part here, which we call the polar axis of the mount, aligns with the spin axis of the Earth, this telescope will only need to drive the telescope to track any object in the sky. because we essentially know where everything is in the sky, for the bright stars, the galaxies, and things like that, especially objects that are observable with these instruments. So we have a catalog of positions. And for those wandering stars, the planets, and the major comets and asteroids, know thousands of positions for those and how they move through our inner solar system and outer solar system. We have a catalog that we can essentially say, I know where I am on the Earth. I know what time it is. Go point to this part of the sky, and that target should be there. So here's the right ascension axis, and this is like the up-down or the declination axis here. So in this instrument, there's a motor. This is the right ascension motor with an encoder which sort of tracks where it is in its travel of this 360 degrees. And the same thing here for the declination. There's an encoder here, and on this side is where the motor is. And I'm going to turn on the power supply shortly to show you how it moves. Actually, why don't we do that now? Why that comes up, I'll contact the telescope and then tell it to go home. This is like the initial positions of what's the 0 point upon which the positioning system sort of figures out, okay, where's my origin or my 0 point? And there's actually code in here that says, okay, drive all the way one direction. If I don't find it there, drive in the other direction. And if it fails in doing that, it does it again and then again. And that's the home position. And then the stow position, which is going to now, we point it at the ground, because when it's not observing, we don't want the telescope pointing up at the sky, and I'll tell you why in a minute. And now here's the motor for the right ascension trying to find home, and that can actually spin 380 degrees. But you say there's only 360 degrees in a circle. Well, there's actually a little limit switch in here that allows it to over-rotate and then go back again, so that it can position itself optimally without having to flip the axis. So you might hear that slight motor moving. And these are stepper motors for you gearheads out there.
And excuse my, I hope I'm not making you sick by moving the camera around here.
So that's the positioning system. Now I'm going to manually move this with my hands and show you the front of the telescope. This is actually a 2 optical system. The large hole is the main instrument, the main telescope, which has a 6-inch mirror in the back, which, if sometimes we can figure this out. See, there's the mirror. See the reflection there of the screen? Okay. And a secondary mirror right where this little circle is at the front corrector plate. This is called a modified Maksutov Newtonian design, because the light gets gathered in through the aperture, gets collected by the primary mirror back here, redirected this way, and right behind this little circle is a pickoff mirror, which is just a flat reflective mirror that redirects the light this way, because right underneath these cooling fins is where the detector, the digital detector is, that captures the image. But that's after it goes through a slight focusing lens, the shutter that opens and closes that controls the amount of light that enters into the detector, and a filter wheel that allows you to choose either clear, no filtration, or the red, green, blue filters for making color composite images, our neutral density filter, which cuts down like 99% of the light or 96% of the light for those very, very bright targets. Before it gets to the digital camera, the digital detector here. Now you can see from this vantage point here, possibly, there's this tube right here, and that's the finder camera. All that is a wide field camera lens with the chamber that holds the digital detector, a shutter, and a neutral density filter. There's no color filters on the finder. So I'm going to trip the finder, and you'll hear what that sounds like. And that was 1/10 of a second exposure. So the filter gets pulled out of the way by the solenoid. The shutter opens and closes real quick. The light gets passed through the wide field camera lens to the digital camera. It's actually getting digitized now and communicated through that cable back to its host computer. And I'll do that again. Open it up longer. You can see at the front of the tube here, look for the shutter to open and close quick.
Yeah, I think I saw it.
Okay. And we'll see. This whole system was designed to actually look at any target in the sky, take as long as a 60-second exposure, and then get ready for the next observation while communicating that data to the host computer and sending it to the servers here in Cambridge within 3 minutes. And hopefully we'll get that down to a shorter one. I guess something's not connecting up right here, and that's the reason why it's in the lab.
Frank was hoping to show you the picture that just got sent to the, but
and it's confused between what camera it's using, because this is the finder camera here, and this is the wrong aspect ratio and image format, because it's thinking that it's looking at the main imager, but it's actually looking at the finder imager. So there's the main imager, which is looking at nothing. Then I'll go back to the finder.
do you want
It's quick. I'm pointing at a book. So that wasn't too long and saturated. But this is the control software that controls the operation of the telescope itself and all its subsystems. And this is the interface that takes the data. And here it's looking at a bookshelf in my lab with some saturation here. Notice the values here.
You can see that the software that controls the telescope, I don't know if any of you had Macs, kind of in the Mac Classic age, but you could kind of see the interface is of that era. So, so it's interesting that just as the Hubble Space Telescope actually had, has legacy software code on it from 1990 when it got launched, our MicroObservatory telescopes have some old software code as well, still running them.
These were originally developed on Mac 2s, if people know what that is. And so this was a picture of the finder with the finder camera and the finder telescope, that smaller hole on the aperture, which is a 12-degree by 9-degree field of view, and it was looking at books and storage boxes in the lab. And a fluorescent light that's saturated here, which is pegged at a pixel value of 4095, and darker titles here is at 1835, and the binding of this one was 1825, etc. So similar to when we look at the moon or galaxies in that, when you look at terrestrial targets like this, this is some of the ways that we test out the detectors in the lab before we bring it up to the roof to test out further to make sure that they are functioning in the field. Now we're about to dismiss students for the day. I have to assist with bus. Okay. Yes, we're recording this. So whoever, David. So we're recording this. You could view this later.
So Frank, how about if let's kind of just take a look at the guts and then maybe see the shutter.
The shutter. Okay. Yeah. So back to the components.
You might want to come around.
Yeah, come around here. Inside the telescope itself, there is a central processing unit that's behind this board here, which actually looks like this board. This is the central microprocessor, and this is the Ethernet chip, original Ethernet protocol, and then some memory banks and some programmable chips. And that's essentially like the mothership, the mother control boards. And these are what we call daughter boards. This board here controls the finder or the main camera, the communication between the CPU and the digital camera itself, and clocking it, telling it when to download the image, when to clear the CCD chip to get ready for the next image. This board here controls the solenoids, some of the motors, because there's a motor for the slight focusing lens, there's a motor for moving the filter into position, there's a motor for moving the declination, and this small board here is for the right ascension. It's a much beefier motor, and so I have to dump heat for driving that stepper motor. And you notice these little plug-in boards here. Through the years, some of these chips that are now were originally designed about 30 to 40 years ago, are not made anymore. So we actually brought in one of the original designers, and he made new little daughter boards to have the same function or more capability than the original chips. And so this here is, let's see, this one here is the declination controller. This here is the focus motors, little daughter board, and these big capacitors control the new shutter, or fairly new shutter on the main camera.
So all these components, if any of you have borrowed our Little Bits kits, the design engineering challenges are meant to help kids think about how you design electronic circuits that do these things, that can run a shutter, move a shutter, or move a motor to aim the telescope or to turn a filter wheel. So why don't you show us the
go over there.
Shutter circuit, or oh.
So this is the camera head that has been extracted from Ed, who's soon to come online. I just have to open it up and dust it out. But here's the finder camera with its lens and its chamber. Here's the entrance point for the light into the main detector, which has a focusing motor. There's a little lens in there, because with the change of temperature, the focus point, as all this metal expands and contracts, and the focus point changes slightly. This motor moves this filter wheel, which is in there, and then this is the shutter here, and inside this chamber is where the CCD camera is. I'll show you a prototype board for the shutter, because we replaced the shutter. It used to be a solenoid that used to have this thing that slammed in and slammed out, and that was one of the big failure points. So we were able to budget some of our money, bring in one of the original designers, and this spread of what we call breadboards is the original prototype design for controlling these new shutters. This is the shutter. Some of these are found in commercial grade shutters on photographic cameras. And the whole purpose of this is to power this coil, and there's permanent magnets. And as you power that coil, it opens, and then you power it again to slam it close. And we can control this to a hundredth of a second with this new shutter, whereas before we could only control it to 500ths to 700ths of a second. So I'm going to turn on the power supply to this board because I have a different shutter here, which you might see. It actually has some burn marks. Let me pull it out of this. And so it goes through a routine of, can it open up quickly, slightly longer, and longer. You might see some shininess and some white marks on it. This shutter failed in the field, and what had happened is that the computer crashed while the telescope was pointing at a daytime object. And during that time, the sun drifted through the field of view, and the intense sunlight burnt the Teflon that was coated on this very thin stainless steel metal and vaporized it. And that Teflon happens to be vaporized into white powder, by the way. So that's where the white powder comes from.
Great.
So this is a failed piece. It works great in the lab, but it doesn't work that great out in the field when the temperatures can get upwards of 100 to 20 to 130 during the summer in Arizona, to temperatures down below zero here in Cambridge during the winter. So there's that.
How about the CCD?
By the way, this whole circuit got reduced to this little daughter board. Okay, there is power supplied here, and we grab power from different parts of the motherboard. But that whole controlling circuit for the shutter is reduced down to this, and we could even have made this smaller, but we wanted to be able to plug in where the old trip used to be. So the wonders of microelectronics. Now, the detectors, what do these digital detectors look like? So here is the finder's detector. And it's just that little shiny piece in the middle of the bright colored frame. And for comparison, here we are. This is the main detector on the hand that I'm shaking. Same thing. It's that shiny part right in the middle is the actual CCD, charge coupled device, digital detector with all the little gold pins here that get connected. And this is protected inside a chamber with no dust, no or very low moisture. I pack it full of desiccant to suck the moisture out of that chamber. And we also cool this down because electronics work a lot more efficiently when they're colder. For imaging devices, that's important because if the temperature increases, the heat in the device itself creates a false signal. So it looks like it's brighter, but that signal is not from light falling on this detector. It's actually from the heat in the electronics itself. So one of the reasons why we encourage you to use the dark calibration frame for advanced imaging is to subtract out some of this electronic noise, some of this thermal noise.
And in fact, if you've taken images from the Arizona telescope in the summer and then taken other images in the winter, and you look closely at those images, you'll see there's a lot less hot pixels, a lot less of that noise in your winter images, just because it's easier to keep the detector cooler.
Right. And if you actually float over the dark sky of your images, you can actually usually tell quickly if this was taken in Cambridge, where it has a brighter background sky due to the light pollution in this urban environment, versus the more pristine skies in southern Arizona.
All right, I think we're gonna stop. Well, we have a question here from David, who wants to know how many pixels are on the main detector, Frank.
On the main detector, it's about a 1.5 megabyte camera, okay, and we actually bin the original pixels 2 by 2, so that we make super pixels to make that 650 by 500 image. But in the zoom mode, where we only read out the middle part of the image, if we didn't have a zoom mode and tried to do non-binning, it would be 1,000 pixels to 1,200 pixels by about 1,000 pixels in the vertical.
Yep.
We bin it because that allows a fuller well, which allows you to see fainter objects before you reach saturation.
Right. Are there other questions that Frank can answer about the telescopes or how those work?
Any questions whatsoever?
I was curious about the pixel array on your finder too. What's the difference?
So that array is a 700 and about a 760 pixel by 512 pixel array. We don't bin those, but since that has a wide field camera, its scale per pixel, as opposed to being just over 5 arc seconds per pixel, that scale is 1.1 arc minutes, or about 60 times of the sky is imaged on that one scale. And notice that we use the same size images for both detectors. They're both 650 by 500 pixel images.
So when you open them up in JS9, they look the same aspect ratio, but the resolution is much different.
Right.
I see.
So we are cutting off some of the columns and rows to make that aspect ratio and get you a 650 by 500 image, regardless of which imager you have, including zoom on the main detector.
Oh, okay. Thanks.
Yep.
Any questions about filters? You usually get questions about filters.
Yeah, so when your students are using that interface on the Youth Astronet portal or on the main MicroObservatory page, and they're choosing the field of view, they're choosing between in the image of the telescope that you're looking at. Actually, can I highlight that? I think I can. They're choosing, if you see my cursor, this is the wide field. They're using this regular camera, and this is the main, when they choose the main regular field of view. When they choose filter, they're actually selecting that filter wheel that there's this thing that Frank pointed out here.
There's 8 filters on this disc, and this stepper motor, which has a geared serrated edge, this motor moves them into position underneath this focusing lens. They're 1-inch filters, and you say 8 positions, but there's only clear and neutral density and red, green, blue. Well, we actually have one that there's no hole. So that's the dark. We block any light from entering in towards the detector, and that's how you get the dark images. Another one's an infrared filter for the near infrared, and another one is clear for future use.
And then when your students ask for 1 second exposure, they're getting this thing to open just like that for 1 second. And so your students are actually controlling these physical bits. Their requests get communicated to the telescope to control all these circuits that control those physical things. So I like to point out that kids are really, this is a real instrument at the other end. The images they get are the result of a real machine. So I know folks, I want you to know that if you want this kind of tour where your kids can ask questions of Frank or about the telescopes or learn more about the technology they're using in Youth Astronet, this same webinar is available for them. And I think we're getting to the end now, so I will leave you with, I think the deadline for entering the Me versus NASA contest was on Friday, but if you have students who want to enter, I think we could take submissions this week. So we wanted to remind you of that. And then I wanted to leave you with a challenge that we can talk about, which is I have here 6 images from late February and early this month of Uranus. And it turns out I just discovered this I hadn't really realized it previously, but Uranus moves a nice little amount, 100 pixels or so, or 50 pixels along each night. And so I was able to make an animation of Uranus. It'll typically be the brightest thing in the field of view, so you'll know how to identify it. And I use the blink and shift tools with JS9 to make this animation. And so that's your challenge for trying animations. And if you have questions about it, you can post them on the Moodle, and we'll also be creating some short tutorials for making animations. So thanks everyone for joining.
Thank you.
And we'll see you on the Moodle.
Yep.
All right. Let me see. How do I? Somehow here I will.